Okay, good morning, everybody. My name's Scott Miller. I'm with TECA. So, I'm going to talk about hydronics for, an hour or so. And as we go through, it's an overview, basically, and best practices. There's all sorts of ways to do hydronics, which is hot water heating, radiant floor, and otherwise. We could do it where we just have questions at the end of everything, or if you'd like to put up your hand if you have questions as we go through. Not saying I can answer them all, but put up your hand, we can give it a try. I don't mind stopping. It's better than, I think, taking notes and waiting till the very end. Okay? Okay, start off with the code. BCBC, the energy code, 9.36.34, piping for heating and cooling systems. The building code would refer, when we talk about hydronics, to the CSA standard, which is B214, installation code for hydronic heating systems. Most municipalities have adopted our TECA guidelines, like I say. And when I say most, Vancouver does not do any inspecting of heating, but however, West Van, Surrey, Langley, etc., all use our hydronic guidelines. North Vancouver. Other good publications on it was, of course, ASHRAE and the Hydronics Institute, great sources of information when you want to talk about hydronics. Okay, different types of hydronic heating and cooling distribution. High temp baseboard and low temp baseboard. This is the overview of what we're going to talk about here. So baseboard, it's boring, but let's talk about it anyway. Fan coils. That's hydronics to heat forced air. Radiant heating, all kinds of radiant versions, radiant panels, or radiant wall, radiant ceiling, radiant floor, radiant cooling. Boilers, condensing, non-condensing, electric boilers, combi boilers. Heat pumps, that's a big thing, complicated issue. And if we get to it, solar thermal. Controls, that's kind of a critical thing, and it's a complex subject these days, so I think it's worth us just chatting about it. Domestic hot water heating, I don't know if we'll get to solar once again there, but we can chat about it a little bit. Okay, so hydronics. So I'm more of a wet head. David and everybody else today are the airheads. I'm talking water, they're talking air. So, which is better? I don't know. Was one better than the other? That'll be an arm wrestle. Well, let's talk about the energy utilization right off the bat. If we look at, you've probably seen these little circulators. That's a little wet rotor circulator right there on the left-hand side, right here. If we think about the energy it takes to move water, there's a reason that water is used to move energy. It is good at moving energy. It used it for years. I mean, when you consider a power plant, what do they cool it with? Is it air or is it water? I can guarantee you it's water. So your typical radiant-based 3-speed circulator to move 53,000 BTUs. Now what is that? Maybe, 3,000 square foot house around here? You could circulate that whole house with one of these. Most likely, and I'm talking using radiant, fan coils, whatever it is you want to use. You got to move the water, you got to move that many BTUs. That circulator will do it. So we're assuming 7 GPM, gallons per minute, at 12 feet ahead. That would do a radiant system right there. So that's a lot of pressure drop, actually. So we're forcing a lot of water. Even having said that, we use 609 BTUs per watt. So compared to forced air, if we're using the same amount of loading, so 53,000 BTUs, we're transferring the same amount, but to run a 3/4 horsepower blower is using significantly more power. So this is the beauty of hydronics. It's a much easier way to move energy around. High temperature baseboard convectors. Okay, they require 110 to 190 degrees F to operate. At 110, they're pretty much doing nothing. At 190, that's actually, if you look at the material, the engineering data, they size the things at either 180 or 190 degrees. So that's hot water. And forgive me if I talk Fahrenheit here. We can switch to Celsius at some point, but it's uncomfortable for me. Uh, so all of the design criteria is around 180 degrees. So it's smoking hot water. So would we use a condensing boiler with a baseboard system if we had to run that all the time? The answer to that is no. Condensing boilers want to run cool to be efficient. People call them radiators. Over there by the wall, there's a radiator on the wall. It's not a radiator. It's anything but a radiator. It's a convector. Oops, back we go. Yeah, so here it is. This is what happens. Oops, sorry, hitting the wrong button here. So cold air comes in, gets heated up by the aluminum fins. You've seen this a million times. This is all convective. This plate in the front is really not even touching this. Sure, you might get some radiated heat from here, but realistically, it's a convector. You're heating air, and it's migrating up the wall, and so you're usually using it on the perimeter. So the positive of using baseboards is, it's inexpensive. To actually buy that baseboard we saw per foot is really not expensive. It's easy to zone. Well, you guys are like electric baseboard. You have thermostat in a room that operates a baseboard. It's easy to zone. Large BTUs per foot. Well, it's got large BTUs per foot. When we consider we're operating at 180 degrees F, then if 1 foot gives you 600 BTUs per foot, that's pretty good. But we're running at 180 to get that. So it's an intensified amount of heat. Of course, we're going to talk about radiant later, which is going to take this whole room to offer the same amount of heat as a baseboard would do. So obviously the intensity of heat is a lot less with radiant. Negatives, well, there's a few of those. Unappealing, no offense, but it's not very nice to look at. And they're difficult in a room with furniture and drapes and windows and so forth. They're noisy. I mean, I think we've all probably been in a room that's heated. I mean, electric baseboards are one thing. The hot water baseboards do have an expansion factor, so those aluminum fins we saw will you hear that tink, 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 tink with the expansion. There's a bit of noisiness that goes along with them. Inefficient heating distribution. Well, okay, in this room, if we were to put a baseboard right over there, what's going to happen is that cold air is going to come up and it's going to rise up here, and then it's going to just swirl around here and kind of hang around there because we're heating air convectively. So not the best way to heat a room. It's mostly used in perimeter heating below windows, so it'll form that warm curtain. But as far as keeping the room comfortable, it's not so good. The airlock, maintenance-wise, they're notorious for getting little airlocks because you come out of the floor and you rise up and you go over and you drop down again, and they do get a little bit of air, and you can often hear the air flowing through there. So they've got little air vents on them. It can be messy to get rid of that. And they're difficult to clean. Okay, and then we said, well, now that our heating appliances are becoming more efficient, and we want to, in order to keep them efficient, we have to run them cold or cooler. So let's use a baseboard that maybe we can run cooler. So low temperature convective requires water temperatures from 100 to 160. So that's on the higher end. So, I mean, how do you make it so? Well, the other one, we just had the supply in one end and the return out the other. Here we have the supply and the return in the same baseboard, and look at all the fin tube we got in here. Lots of aluminum heat transfer surface. So we can reduce our supply water temperature because our heat emitter is more powerful. Having said that, we still have a convector. And then you got these rascals here. I don't know if you've seen these. These are made of solid aluminum, actually. Very low water temperature, so it's a good match with heat pumps, which produce low water temperatures, or condensing boilers, which love low water temperatures. But this is actually meant to replace the baseboard itself. So this is, it's painted sort of white the same way baseboards are. I'm sure you can paint them as well. They have corner connecting units, and they actually offer a lot of heat. And truly that is now more of a radiator than a convector. So again, you're going to really have to analyze a room. How many BTUs a foot are you going to get out of that? I mean, is it a solarium? That's probably not going to do it. Yeah, there's lots of rooms if you actually did put that in as baseboard. I've done it once. It was pretty cool. And I love the idea they use low temperature heating and they radiate heat, so a little more comfortable. And you've done the whole perimeter. Solid aluminum. Okay, fan coils. Another way to get hydronic heat around a building. So a fan coil is basically a box with a fan in it and a coil, hot water coil. So what we're doing now is using the boiler or water heater or what have you combo system, and you circulate water to the fan coil, to the coil, and you turn on the fan, and away you go. You've got yourself a warm air, forced air system. So it's mostly used in applications with boilers or water heaters, instantaneous or otherwise. So let's say you had some radiant floor in a basement, but the rest of the house wanted to be forced air. Maybe you needed cooling. What you'll have is a hot water coil in there. Why have two appliances? Water temperatures are a little higher there depending on what result you want in air temperature to combat your heat loss. But supply water temperatures between 100 and 180 basically. So obviously at 100 degrees it's a warm day outside. And why not put chilled water through them if you happen to have a heat pump, and it reverses the cycle and now it's providing cold water instead of hot water. You've got a fan coil, why not have chilled water go through there? Now we've got air conditioning. So yeah, like I say, you could have, let's say, a combi boiler, do a little bit of radiant, do your domestic water, and set up a fan coil to do just straight ahead forced air in whatever zone you want to choose. It's also good for makeup air applications. Now, makeup air comes out a lot. Our ventilation code says, and I know you guys have come across this, everybody wants the 1000 CFM kitchen exhaust, but we've got a B-vented fireplace because that's the one they wanted. So you got 1000 CFM going out. The code says, thou shalt replace 100% in any naturally aspirated fuel-fired appliance in the house. You have to replace 100% of the exhausted air if it exceeds 1/2 air change of the home. So this happens all the time. 1000 CFM of exhausted air is a mighty big home to not have to provide makeup air. So when you have to provide makeup air, it's quite a bit. Thanks, David. So just to finish the makeup air thought, it takes power. So there's two ways to do makeup air. You're bringing in outdoor air. So how are you going to heat that air? You can devote electricity to it. Some people put in electric furnaces. There's modulating electric specialized makeup air units. But when you talk 1000 CFM, that's like 7 kilowatts. So that's a lot of power required to something that, I don't know, is it that important? If you already have a hydronic system, then why not consider using a fan coil for that? So these guys here, hot and chilled water, whatever you want to use in there. You see it's got a condensate pan right there. So you just pipe it into your hydronics. So these things you put in closets, or this is a rather large one. They make them as shallow as about 9 inches thick. So if you wanted to put it in, say, a master bedroom closet, drop the ceiling, something like that, you could do that. Or in a mechanical room, however. You see these probably most often. It just looks like a household furnace, but there's your hot water coil down there and your fan up there. Pretty simple idea. Again, that you often see that standing beside a boiler or a combi boiler. Okay, another way of doing things. Back to radiated wall form, radiant wall panels. Let's just move forward here. So these things are used widely in Europe. Everywhere I've been in Europe, I've seen them. Again, they call these radiators, but if you really look at it, a lot of what they produce is a convective heat form. Way better than a a hot water baseboard. These things are using a lot lower temperatures, but it offers a more comfortable sort of experience because a lot of the heat that comes off of that is a radiated style of heat. So it's warming your body and not the air, and you're experiencing the air convective currents in the room. Easily zoned thermostats. You put a thermostat on the wall and connect it to a zone valve. You can have manifolds in a closet that go out to these things that are mounted on the walls. You can also use a local zone valve called a thermostatic valve. So, yeah, we wouldn't use them for cooling. There's towel warmers. That's one way to do it. I thought this thing was kind of cool. Hydronic bench. If you look right here, there's your balancing valve, and that's what's called a thermostatic actuator right there. So it's sensing the room temperature, so you just turn that thing to whatever you want, 20 degrees C, 70, and it modulates the flow of the water through there. So that's just one big radiator. There's all sorts of sizes and shapes. Any questions so far? Yeah. Go.
I guess going back to the makeup area.
Yes.
For the kitchen fans.
Yeah.
Would 1,000 CFM be the cutoff point as to, okay, below 1,000 you wouldn't need makeup air, and above 1,000 you would?
No, the way it works, if you have a naturally aspirated fuel-fired appliance, which is, and David could talk your ear off about this stuff, any naturally aspirated fuel-fired appliance, so fireplace, wood fireplace now, a B-vented hot water tank, a B-vented furnace, anything. So anything that's going to draft air out is going to potentially, if you turn on 1,000 CFM, is going to backdraft that. So, and that obviously could cause issues with health and so forth. So naturally aspirated fuel-fired appliance of any sort in the home, and you have to consider makeup air if you exceed 1/2 air change of the home. So what you do is you calculate the total cubic footage of the home, divided by 60, divided by 2, and that'll be 1/2 air change of the home. So I can tell you the average 4,000 square foot house would be about 300 CFM. So any single exhausting appliance that exceeds 300 CFM in that home, thou shalt replace 100% of that air tempered. So 1,000, I was just using it as an example, 1,000 CFM, I mean, your common household furnace is in around, 1,500 CFM, 1,200 CFM. This is what you're exhausting out of the home. So you're way over the air change limit on a 4,000 square foot house at 300 CFM. So really, golly, anything that's over 400 CFM is going to be a problem. Your kitchen exhausts don't have the best rating system. They don't know how much ductwork you're putting on it. So there's two ways to do that, and David will, or Terry Redier will actually get into that this afternoon more specifically. But if you're after a kitchen exhaust fan and you have a NAFA appliance in the house, then you are looking at makeup air in one form or another. So probably best to avoid the situation. So let's say it's a non-NAFA house. Well, all of my fireplaces are direct vent, so it's not naturally aspirating. It's communicating only with the outdoors. My furnace is high efficient, so it's got plastic venting. My boiler's high efficient. I don't have a wood fireplace, never wanted one. Okay, so maybe we have a non-NAFA house. So you actually don't have to put in makeup air. So we can put in a 1,500 CFM exhaust fan. Maybe you do that, but really would you? That's quite a negative. And we were talking about this earlier. You go into a restaurant and you got to pull the door open, and it's just, oh my God, because they're running such a negative with their exhaust fans. That is certainly the case. So that air will come from somewhere. You put 1,000, 800, 600, 1,200 CFM, very common these days. That air's got to come from somewhere. So even though the code doesn't say you have to, maybe you want to think about it anyway, because you're pulling air in through the skin that maybe you didn't want to do. Any other questions? I hope that answers the question. Okay. radiant wall. So we looked at radiant panels. Now we have radiant wall. Anybody ever seen this done before? It's actually used very little. I mean, it's got all the good points of radiated heat because you've got a large surface area, a whole bunch of walls. Now, I'm not saying it's your first choice for a radiant, but we were on the radiant panel, so I thought we'd go right to radiant wall. It's an option, and we'll talk a little bit more about it. So for supplementary heating requirements, let's say it is a solarium here. Let's say we got glass, and I got a nice tile radiant floor, some kind of nice tile there, and we really want to heat it with radiant floor. Of course, it's the best. But I have a limitation. I can get maybe 35 BTUs a square foot out of that radiant floor when it's smoking hot. I have surface limitations that I can't cross. We'll talk about that later. So I'm out of floor space. What am I going to do? I told you I don't want air in there. Okay. Well, how else are we going to get some supplementary heat in there? Well, there's the fourth wall. One great big exterior wall or interior wall, 14 feet high. Why not? Why not fill that rascal full of radiant heat? Let's add it to our heat calculation. There you go. So as a supplementary form of heat, I kind of like it. So there's obviously drawbacks to it. It looks like somebody's retrofitted it in here. Right here what we have is heat transmission plates. Of course, it's going to be difficult to hang a picture on this wall. That's a drawback. But the heat transfer plates with radiant wall, we're trying to go through this drywall. Is it the best conductor? Well, it's not the worst, but it's also not the best. So heat transfer plates make an amazing difference. An absolute must, I think, in most of these applications. So if it's meant to be supplementary heat or just heating the room, why not? You know, another application, what about fireplaces? A lot of times you'll see whole walls of masonry, decorative stone and so forth. What a great place to put radiant wall as well. That'd be a great heat emitter. Again, you'd still use fins, but just something to keep in mind. You can be creative with it. Ceilings. It's more common than you'd think. Again, supplementary heating. If you don't like the idea of the walls, then what are you doing with the ceilings? Seems to me there's opportunity there. There's just as much ceiling area usually as there is floor area, if not more. So again, heat transfer plates. It's a must. So that's what they've used here. So this is just PEX pipe, of course, run through, and heat transfer plates nailed to something. And then over that, the drywall will go right over top of that. No problem. As the drywaller screws it in, he can see where the piping is, and as long as he's paying attention, he's not going to put a screw through that. Lots of opportunity for ceiling radiant. Again, another version of that. Nice, neat job there. Somebody's doing a perimeter there. That looks like a supplementary sort of application. I'm not saying it's the best place to be radiating your heat from. I'd rather have it from the floor, personally. Again, works best with heat transfer plates. Anybody ever seen these rascals? Ceiling radiant. This is a German product, and it's called capillary mat. It's quite interesting. The Olympic Village, for example, chock full of this. In Europe, what they do is plaster this in the ceiling. So these are very fine tubes. Super fine. They're like 1/8-inch diameter tubing. You can use them for heating and for cooling. Made out of polypropylene. They're quite popular in Europe, believe it or not. So you get the heating and the cooling. Well, it's not the worst case scenario for cooling when you think about it. I've actually put some of these in a commercial application before. They're polypropylene. They don't have an air barrier, so they do tend to entrain oxygen into them. So you have to have air removal systems, like any other radiant system, but they're a little more prone to it. And of course, pumping requirements, because the tubing is such a small diameter, it's quite a bit to pump through there. The Europeans love them. I've seen a few applications. Integral Engineering fell in love with them for a while. Care homes, places where you don't want to have a lot of noise associated with cooling. Radiant ceiling panel, yet another way to do ceilings. And commercially, these are actually quite common. Oh, what's happened to my aspect ratio here? So mostly commercial applications. And in commercial applications, so for office towers, commercial buildings, Coquitlam Recreation Center, I noticed they are using these. So along the perimeter, this thing is just a solid aluminum emitter. So again, you can use lower temperature circulation here, which is good. So that is indeed now a radiant panel, so it's radiating heat straight down. Probably not a lot of use, I don't think, in residential application, but I think it's good you know about it. Heating and cooling. Then there's radiant floor. Probably the best for comfort of everything we've looked at so far. Easily zoned. So we've got the wet systems or in-floor systems with the poured concrete. Dry systems underfloor. When you consider heating types, I mean, you're not having to get forced air ducting around. You're not creating drops, of course. We all know that. You don't have baseboards on the walls. It's a good way to go. So, I'm not saying it's inexpensive. Of all the ways to heat a building, it's probably one of the more expensive, particularly when you include the cost of the concrete and whatever structural considerations around having concrete floors. And again, it can have heat output limitations. Your classic basement. So here we go. What are we doing? We're just going to tie tubing to wire mesh. There's your manifold there in the middle. Everybody's done this, I'm assuming. If you haven't done this, put up your hand in a home. Okay. Polystyrene. We'll talk about the insulation shortly here. R12 is what we're normally asking for. Best practices with heating a slab. Do you guys use chairs when you put wire mesh on there? Okay. How many guys do? Just show of hands, I'm just wondering. Okay. All right. So it's not the end of the world. You've got your wire mesh. Your wire mesh is sitting there. And if you just left it there, I mean, it folds enough. If that's going to be a 4-inch slab, it's going to be what? Maybe in the bottom third of the concrete layer. Not the end of the world if that's the way it works. Best practice though, why not put some chairs under it? Get it up into the middle or closer to the top of the concrete. I see this a lot in installing floors on wire mesh. So you're usually putting the wire mesh there only to hold the radiant. I don't know if it's required structurally. Well, the guys go around and back in the day use a lot of wire ties, like rebar ties, and just crank on those, or even now with the nylon zap straps to really just pull on those. That pipe's not going anywhere. Really don't need to do that. I know it's tempting for everybody to just tighten it right down. It's only really on the turns to hold them in place, and even then you don't have to really cinch them. They've had some issues in Europe that have been reported with people over tightening these things. I won't go into that detail, but I can tell you that when you tie this stuff down, obviously you want to have your tie wrap on the side and you want to snip it. make sure you, when you do it, you put it on the side, because as the guys do come along, that zap strap is going to stick up probably, what, half an inch maybe off the top of the pipe, and that's a half an inch that could potentially poke through the concrete. So put it off to the side, don't tighten the heck out of it, and snip it off. Simple as that. Leave some looseness there. Pressure testing. We all know we got to do that. We all do that, I'm assuming. And we all should know that we have to leave it on while the pour is being done. And I don't know, maybe you can remember what the pressure test was too, or just take a little felt pen and put it right there on the needle, so if somebody needs to check it somewhere during the pour, they can just glance at it, yeah, it's good. I mean, it's not often that we get leaks, but it is certainly part of the code that we do pressure test. You can use, it depends on where you are in this province. Maybe you don't want to use water. It's nice to use water for hydrostatically testing, or use air. Either way, it's up to you. Obviously, if you test with water and it's October 24th and it's going to freeze in a month and you're not going to have that house done, you probably don't want to test in that case with water, because you could potentially freeze and snap that pipe. And also with respect to pressure testing, it's worth talking to the concrete guys in the concrete code. There is a standard around pressure testing of piping actually that's in slabs. So it's beyond my scope, but as far as I'm concerned, 1.5 times, minimum 45, 60. And we'll talk a little bit more about pressure testing here shortly. Okay, use slab edge insulation. Who does that? Show of hands. Slab edge insulation. 2 guys. 3, 4, 5. Okay. We know that we have to use insulation below a heated slab. I'm assuming everybody's aware of that. If not, let's make it clear. The building code says you have to insulate below a heated slab. R12, it's the discretion really of the municipality or the building official, but you're going to wind up with either R10 or R12. Which is fine, and David will really dive into this subject when he talks about F280 and the nature of how to insulate basements and the calculation of it. But let's just say we're insulating the whole slab, which is good. If there's a lot of moisture under there, and I mean a lot of moisture, if it's soaking wet, how about you think about not putting radiant slab down there, because insulation is a function of time, really. It's going to pull all of that energy out of that slab. So it's good to understand what your water level is below a radiant slab. If there's too much water, maybe don't do it. How about that? Otherwise, the next most important thing is certainly slab edge insulation. So this is kind of what I'm thinking here. We know we got to put it on the bottom. What about the side? There is so much energy that's lost through the edge of the slab, it's ridiculous. So is this insulation? There, as a requirement, I don't see what the requirement is. All I know is that it's a really good idea. It's a better idea than insulating the middle of the slab, in fact. Because here you have conduction with, of course, not just the outside wall in this case, but even if it's an inside foundation. What you're going to do is suck all that energy into this monolithic structure, which is into the ground. So kind of makes all this stuff useless if all the energy is going out this way. So whether or not it's a piece of Donnacona, whether it's 1.5 inches or 1 inch, ½ inch for God's sakes, anything in there to stop that energy transfer to the structure. So I highly recommend, wherever you can, isolate that slab. And I know, and the reason I put this 45-degree angle thing here is because if we went straight up, which would be better, obviously, then you're going to say, well, what do we do about this little section here of insulation or whatever it is? Answer is, I don't know. All I know is it's a good idea to have. So if this is a compromise, how about that? Any questions about that? Okay, moving right along to suspended subfloor, and we've seen this a million times. You guys think that, what is that? Is that lightweight concrete or is that gypcrete? I honestly can't tell from the picture. Yeah? So slab thicknesses anywhere from 1.25 inches to 2 inches. I don't know you get away with 1.25 inch slab using lightweight concrete, but Gypcrete says yes, we can do that. They're even talking about 1 inch thickness. Of course, we need some cover over the pipe. In this case, this pipe is 1/2 inch, which means it's 5/8 OD, and here we have staples. So that's another 1/8 right there. So we need to have some cover over this pipe, at least 1/2 inch of cover over that pipe. I'd rather see 3/4. So do what you will with that. I know mostly everybody in this room has probably done this 100 times. Okay, fastening. So in this case, it's staples. You could use Talon clips if you want, and we'll see those in a picture later on. Usually 18 to 24 inch spacing. Some inspectors will, in our hot water heating code, we say 18 to 24. Some inspectors say 18. You do it every 18 inches. It's kind of up to you in a sense. If that's tested with air, you might get some floating if you're too far apart. If you're 2 feet or beyond, you're going to get some floating there. So 18 to 24 seems to be the sweet spot. Now, when we're talking about testing, let's just go back here. So these staples, how many people have seen contractors use staple guns to staple down radiant? Okay, well that's actually a fairly common way to put your radiant tube down is with staples. So pneumatic stapler, you go along, it's great, fast, it's quick, kapow, 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 and down it goes. The problem is you can miss. Like these get mighty close, and I can tell you that the percentage of staples that actually go through radiant tube is pretty high. And I can also tell you that if you throw 45 psi into that pressure test, that staple could probably take that. You won't even know because it's into plastic tube, into PEX pipe. It may not leak. So if you're using staples, maybe up the ante, 80 psi or so, as long as your concrete is good with that. Don't get me wrong, staples are fine. They're a good idea. It's just you can get a little sloppy, and so somebody should really walk around and look. That's one way to do it, and because you can't really rely on the pressure test. Just make sure you haven't punctured the pipe. Otherwise, Talon clips are safer, just a lot slower. Yes, the gentleman in the back.
If you were to use 80 psi, would that pipe be swell enough that it would break contact with your gypcrete after the pressure is relieved and in normal service?
I don't believe so, and usually commercially it's anywhere from 80 to 100. So our code says 45 to 65, and again, it depends on what the content of the concrete is and so forth. So I think it's worth the risk in this case to increase that pressure test for staples anyway. Well, that's a good question, David. Okay, pipe laying patterns. I don't know if it matters to you guys or not. Serpentine pattern, which is this guy. It's easy to install. So you run up here and you go over here and you know what your centers are from your heat loss. It told you what your centers are going to be. Your radiant design layout will say, okay, let's say it's 12-inch centers. So I run up here, I run back, and they're all 12 inches apart. Great. Here's another way to do the same thing. WVen. The difference is here, if you do it the simple way, which is fine, but you notice you got a lot of fairly tight turns here, like 13 180-degree bends. If you use the reverse, I call it reverse return, also known as W bend. And when you think about it, you got 1, 2, 3, 4 180-degree turns. The rest are 90. So It doesn't really take a lot of planning to do this, to say, oh, let's measure 3 feet over and go over, back, leave room, and away we go. It's not that hard to do, honestly. And you wind up with less potential for kinks. And, as far as the water flow goes, when you do bend the pipe, and every pipe has a designed bending radius, and it's published as Worsbo, Watts, Ray Howe, they all say, well, this is what your turning radius can be, and it'll be so many times the diameter of the pipe. So you have to maintain that. So you won't see people doing, if you see people doing 4-inch centers with 1/2-inch pipe, they've already negated the warranty of the pipe. It's too tight. And so the ends are going to compress a little bit. That's going to compromise your flow. Pumping energy goes up, so forth. So this kind of thing is good. And go the long way. So why would you go the short way and use up all these? Go the long way, for God's sakes, if you can. Unless, of course, you have issues with hardwood floor. If you have, I don't know how much we do it anymore, but used to be 2x4 sleepers when you'd use a 3/4 inch, the actual hardwood, not engineered floor, but actual hardwood 3/4 inch. Often it would go on sleepers, so you would wind up with sleepers here, right? So, that's going to be pretty much the only thing that's going to regulate which direction you run your loops is if you have sleepers for hardwood floor. Okay? And if there is no regulation, why not go the long way? Less bends. So that is indeed called the W bend. Less turns. Here's another example here. So there's a whole room full done like that. These are the W bend. Easy to do. It's actually a little bit better at distributing the heat as well. So, and then the king of the patterns with respect to laying radiant, how about this guy, spiral? Only 2 180-degree turns in that whole mess. One there, one there. Quite a difference. So in these rooms, you have the flexibility of whatever pattern you'd like to use. If we had, for example, if this was solid glazing here, this method is going to be great for distributing the heat throughout the center or right throughout the room. Our heat distribution is good. Our RHWHA TECA guidelines say that the first pass has to be a 6-inch center. So off of the supply manifold, looks like the manifold's over here somewhere, you actually have to come over here and on the outside wall go over here, turn around, come back on a 6-inch outside wall. Doesn't matter the case. If it's an outside wall, it has to be a 6-inch pattern first. Then you can go with whatever your heat loss says. If it's 12-inch, 8-inch, 6-inch, 9-inch, whatever the separation is. But the first pass is always that way. Many guys get failed for not doing that. And some guys will say, well, it was under a cabinet. Was a cabinet on an outside wall? Then, yeah, you got to do it. It's an outside wall. Is it a requirement? Whew, man, that's a point of discussion. Depends on what. If you talk to Upanor and Ray Howe and so forth, I don't know. They don't really think it's necessary. But it's in our code, and the inspectors look for it. Having said that, so in these rooms, back to this example. So if I came off a manifold here, and let's say I did do that serpentine back and forth, that's not a bad way to go. If I had nothing but glass here, a lot of heat loss, why not get that hot supply water there and just run it over there back and forth on 6-inch? Because what's going to happen is it's going to be the hottest there and it's going to fade. You'll see the return water temperature fade and fade and fade towards the middle of the room where you don't really need it. So in some applications, the serpentine pattern, you can utilize that if you really need to focus the heat there and you know you're going to have a gradient of return water temperature. So it's going to be quite a bit hotter over here, isn't it? Way more heat than there's going to be in the middle of the room. We'll talk about that in a minute too, actually. Okay. Then you got different ways. There's different products for installing it. In a retrofit sort of application, it's called Panel Track. All of your manufacturers tend to have this sort of thing. This is like 1/2 inch or 5/8 plywood, and it's actually got aluminum that's built into it. All of these pieces click together. So in a renovation, if you wanted to plunk this down, or in new construction, but I think you'll find the cost a little bit prohibitive. I don't know, you add up the cost of the slab and so forth, and you say, well, this is all I'm doing, I'm going to put my hardwood right on this. Maybe it's okay. I don't know. The times I've worked it out, it doesn't make a lot of sense in new construction. Better ways to do it. But in a retrofit, you want to do a room or two, why not? So here you have thin plywood, so you keep your floor heights low, and then now you're using smaller tubing. 3/8 tubing right there. So higher pressure drop, less heat transfer, and normally what you do is you put like a silicone in there as well, and as you step it down, it keeps the pipe in there. But it's kind of a cool product, actually. I think they use a lot more in the States. This is, if it's the same one I'm thinking of, Schluter makes a product called Becotech, and I'm not trying to push any kind of product. The orange reminds me of Schluter, but the product I'm used to by Schluter is actually just a styrofoam. So what this is, these pucks here, Schluter actually invented it so that when you pour a slab, you get these minute cracks that happen in between these pucks. And the point of that was to say, now we're not going to get catastrophic cracks. We're going to get these minute cracks, so not really getting cracking. So if you're putting tile over this, they're thinking it's the way to go. And then I said, well, for doing that, why don't we organize the pucks so that you can actually fit piping in between and just snap them in there. They're kind of conical there. They've got a bit of a cone shape to them, so the pipe just snaps in there. It's pretty slick. So why would you use that? The one application I can think of, structural slab. Or let's say you've already got a basement slab poured, renovation. You could put that stuff on there. You could also, if you wanted to pour a slab, use this stuff here. The beauty of this is it's actually, overall, it's 1.25 inches high, and the bottom of the puck, so the distance from the bottom of the puck to the bottom of the sheet, these sheets come by 3 by 5, and they just click together. So you glue this stuff down or tack it down depending on what you're attaching it to. You do also get that 5/16 of insulation, which would, let's call it more of a thermal break. So on top of an existing slab, you know, if we're going to pour 1.5 inch slab on another slab, structural slab or otherwise, what's going to happen is you're going to transfer all that heat into the slab. You could have a 6-inch slab. So if we can isolate the two slabs, our response time's obviously going to be a lot better. And we already know what happens with heating slabs that are connected to foundation walls and other structural components. So this is a great way to isolate your radiant floor from whatever's below it. And it's also a fixing. So you're going to do something there. You're going to put wire mesh. You put wire mesh down, now you have no isolation to the other slab. Any questions about that? Sorry, I don't know. I just found this picture. I just thought it was bizarre. Like, what in God's name would you be doing here? You got wire mesh, no insulation anywhere, a little bit of perimeter. It's just no organization, pipe crossing. And look at these, the spacing is like 3-foot centers. I have no idea what somebody would be doing there. I just hope that's a very warm climate. Underfloor. Okay. So, saves the cost of a lightweight slab. Well, we were just talked about the cost of that. You guys would know better what it is than I do. Saves the extra height of the slab. Renovating or otherwise, or whatever the case, there's no way we're putting 2 inches or 1.5 inches on this floor. Okay, well, how about under the floor? Let's think about that. Again, that works best with heat transfer plates, and I'll show you that in a minute. Is it good with hardwood floors? I guess it depends. I shouldn't say it's not good with hardwood. Depends on your hardwoods. Again, you guys would know better than I do, but I think engineers' floors have a way better resistance to high temperature heat, because when we're heating underneath the floor, we're having to heat through a subfloor, so we're circulating higher water temperatures. Because we're heating in a joist space, usually, we've got a lot of downward losses, so we're heating below as well. So we have to take care of that with some insulation and reflective material. Significantly higher water temperatures. There's just no getting away from that. We'll talk about that here shortly. So here's your classic underfloor application. There's your heat transfer plates. That's how you pull the pipe in. It can be messy business. What you do is you run along and you pull all this pipe in, you pull the loops all the way to the end, you leave them hanging there, and then you go along and you staple up all of those plates. So you're winding up, if that's 14 and a quarter there, 16-inch center, then you're around 9-inch on center, which is not bad. But you need to have these things in this application. Now, that can be a little bit noisy potentially. You got to make sure you fasten these things properly. Different ways to do it. Classic heat transfer plate. There's several manufacturers. This one is, I believe that's Rayhow or possibly Watts. Kind of cool. So you'd go along, you just tack this thing in the middle of the joist space and go along and just tuck your pipe in there. But look at the heat transfer with the aluminum to your subfloor. Definitely superior. Anybody ever done this before? Underfloor heating. One? Okay. I've done it. In fact, I did it like this. Things we do. So, no heat transfer plates. Not only that, Talon clips here and here. So once you get nice hot water, and it's going to be hot water because we got to heat the room above, and when you think about how are we actually transferring that heat, Radiant needs to have conduction. Our water flows through the tubes into and the heat is transferred through the pipe into the concrete through conduction, and then we're radiating from there. So if I'm trying to conduct heat from this pipe to this wood, it's a round pipe, so there's really only the top surface of that's actually touching the subfloor, so not the greatest thing. You got to use heat transfer plates. All it does is increase the surface area of this. So if I wanted to heat this space with this type of heating, the supply water temperature that I would have to put through there might even go beyond the condensing boiler's comfort zone of efficiency. So not a great way to, if you're going to go to this length, go ahead, put the heat transfer plates in there. Seen this before too. So what are we doing here? So there's for sure no conduction. This is strictly convection. So we are really using radiant plastic pipe to heat a joist space, and we're hoping that hot joist space is going to heat, I guess, the hardwood floor or tile floor above and radiate enough heat to heat the room above. Tricky business. This I would not recommend. Doesn't matter what your life is doing at the moment. This is just not a good idea. It's too much convection, too much high temperature. And I don't know, if I'm circulating, I'm guessing that'd be about 147 degree water through there, Fahrenheit. What's that going to do to your structure? I mean, is that okay, or are we just going to bake all those joists and you've got things drying at different levels, and then you got hardwood floor on top of that? So if you're going to get into this, make sure you use the best method with respect to heat transfer plates. And if you're going to use plates, we're not out of the woods yet. So, and David, you might want to talk a little bit about this, but so if we're trying to heat through this subfloor and then hardwood or tile, I mean, with tile, it's going to actually work not bad, I must say. So if it's that solarium or that addition or whatever, and you want to just have a warm floor, maybe it's not even heating the room. Maybe it's just tempering the floor. It's not that big a deal, so why not do it? But let's make sure the heat goes that way too, because we are going to get a lot of convection happening here. So the heat that radiates down here, if we put in reflective foil, and it doesn't have to be this stuff, but whatever goes in there, that reflective material is critical for reflecting the microwaves of heat back to the surface we want to heat. And then below that, let's get some insulation of whatever form in there.
Now, Scott, the one on the left is a real sleeper, extremely powerful for two reasons. The aluminum plate, what you call the heat transfer plate, does the obvious of distributing the heat over a greater area underneath that subfloor. But what most of our industry doesn't recognize, it serves additional benefit. When aluminum is a reflective surface on its own is hot, it cannot radiate. So the mere act of putting the aluminum and attaching it to the plywood means that in that area which the aluminum is covered, it radiates almost no heat down. So a far higher percentage of your heat's going up than you would have thought at first guess.
Right.
And the little bit that is radiated from either side of that plate is reflected back up with the foil,
Sure.
giving you a net R28. In other words, equivalent to a whole thick 8-inch bat.
Right. We actually had a professor of thermodynamics really analyze this. And not this foil in particular, just the act of using foil on top of insulation. You've got to have this 1 to 2 inch air gap for sure. There's got to be an air gap. If you put it against there, it's just another conductor. It's not doing anything. You need to have the air gap. So the difference was immense. Having said that, I'm not saying that these foil products are great. Like I've seen some people put them on subfloors as insulation and then go ahead and put a concrete floor on top of that thinking they're doing the same thing. But in actual fact, the effect there is, again, more of a conduction because you don't have the airspace. You need the airspace for the reflective part of it to actually work.
It's a very, very good system that you presented on the left-hand side.
Right. Okay. So now we're talking about all these circulating temperatures. Yeesh. Okay, let's talk about the code. B214, that's CSA. It says floor surface temperature shall not exceed 29 degrees C, 84 occupied areas, with the following exceptions. Industrial spaces, well, we're not concerned about that really. But bathrooms, you could be 91. Indoor swimming pools and foyers. In radiant panel perimeter areas. Well, that's interesting. Apparently, you're not going to be standing in those. Remember I was talking about maybe running a serpentine loop a few times, and that's going to be a lot hotter there. You put your supply water there, and as you work your way in with your tubing, which is going to be maximum 300 feet in length, as it comes in, it's going to cool a lot. So your potential floor temperatures can be quite a bit higher there, but CSA is okay with it. So 95 there, up to 2.5 feet from outside walls. So also mentioned in the ASHRAE standard 55. Any questions about that? I know, your hardwood guys would have something to say about all of these things with respect to the temperature that they want to have their wood at. But as far as human comfort and the CSA code, and as far as we're concerned, that's our limitations for surface temperature. So you really need to calculate the thermal resistance of the material you're heating through. Just because our floor is 91, that does not mean that's our floor surface temperature. We could have a circulating water temperature of 130. So we have to calculate that in. What's our circulating temperature? What's our floor surface temperature going to be? This is all part of doing the radiant design to understand that we're not going past our surface limitations. Okay, any questions so far? Anybody? Anything? Coffees? Anything? Yep.
A question always comes up when you use radiant panel, which is a lot of popularity down here. Can you just make some off-the-cuff comments on the carpets, underlays, hardwood floor, and their resistances to heating the room above?
I kind of wish I had the chart of resistances. That's actually in our document. Certainly, if you're getting into carpets, I talked about hardwood because we're sensitive. We never want to screw up a hardwood floor, obviously. We don't want to overheat a hardwood floor. But when we're talking about heating a room, concrete itself has a thermal resistance, which we calculate in. If you say, well, it's a bedroom upstairs and I'm going to have some underlay and then I'm going to have this wool carpet or whatever, each of these things have a resistive value that has to be put into our calculation software. Now, you can dramatically screw up the ability to heat a room by using underlay and carpet. Underlay is about the worst, and carpet's after that. So it's critical to look at that. And often that's, I mean, you'll find carpet in bedrooms, etc. So it's critical to analyze each room's, if somebody's doing a radiant design for you and they haven't asked you what the flooring is, that's going to be a bit of a question in your mind right away. You know, okay, yeah, they start stapling down the second floor and they don't know, maybe you don't even know what the flooring is. No, homeowner hasn't made up their mind. That happens. But somebody's got to look at that, and our code says you take the worst case scenario. If you don't know, you better allow for the worst case scenario, which is like ugly carpet in there. Who knows, somebody puts that in later. So you have to factor these things in when you're doing the design. A lot of resistance in carpets, sometimes to the point where you cannot heat the room. Radiant cooling, anybody? Okay, radiant cooling. So we all know there's air conditioning that's on right now. If we are trying to cool this room with the wall or the floor, we're not really dealing with the convective air currents in the room. What we're dealing with is it's like you standing by a big cold rock. And what happens is the heat from your body radiates and is absorbed by the big cold rock. That's what we're doing here. So when we talk about radiant cooling, now it's the reverse process happening. You're radiating to the cold surface. Tricky, tricky business though. It's not for everybody. Not for the faint of heart. We just talked about that. So it's cooling, it's not air conditioning. When we talk about the sensible load, we have in the air, we have a sensible heat and we have a latent heat. So sensible heat is the heat that you can sense. Latent heat is the actual moisture in the air. And for the most part, that's the uncomfortable bit. Our sensible load here is, 70 on average, depending on the time of year, of course. And then you've got your latent load, which is your moisture load. With radiant cooling, where you're just accepting radiated heat, you're only dealing with the sensible heat component. Latent heat, the moisture, how can we remove moisture with a radiator? It just doesn't happen. In fact, you've got to go through extra lengths so it doesn't happen. So when you're in air conditioning mode, your classic air conditioner, what have you got? You've got warm air that circulates on the return air. It's say 80 degrees, and it comes back into the return air, goes over your cold refrigerant coil. And it's at that point where that warm, moist air, that's where you deal with the latent load. So the moisture that's in the air, as that air shrinks and cools and condenses, it condenses on the evaporator coil, and that drips off down the drain as moisture. So you've actually removed the moisture from the air, or a good chunk of it. And for a lot of people, that's the uncomfortable bit, particularly if you're in Florida or in Toronto, etc. Here, not so bad. Our latent load is not so bad, but nonetheless, radiant cooling deals with none of that. So if that's what you're trying to get rid of, and if we think about it, in a home, what is our air conditioning load? A sensible load. If you got the solarium, you're going to have sun shining in there. That's going to be a sensible load. But once the place is sealed up, you're cooking in there, you're doing laundry and so forth. We do have a latent load. People are a latent load. So there's a latent requirement to make that air conditioned. So radiant cooling is not conditioning the air. It's cooling the room. To condition the air, you have to deal with the latent load. We're not touching that. Any questions about that? Okay, moving right along. So it's often therefore used with some other supplementary system. So maybe you have a heat pump and maybe you say, I don't care, I got the radiant there, I just want to cool. If I can cool, I can, okay, you can cool. But we're not saying we're going to air condition your home. So let's not talk about air conditioning the home. We're not. We're offering some level of cooling when you get into radiant cooling. So it requires very careful control of supply water and surface temperatures. Heaven forbid we should actually cross the dew point with our relationship of our supply water temperature and the air temperature, the humidity level, and therefore the dew point. We do not want to send 45-degree water around a floor, for example, and have the air, the moisture in the air, actually condense on the floor or anywhere. Wouldn't have to be in the floor. It could be anywhere in the structure, wherever that piping is. It could be in the wall. So very critical to control supply water temperatures. So it actually works better in the ceiling in this case. That's why the Germans like to put it in the Becker mats. And it's also got capacity limitations. The same limitations we have with absorbing or rejecting heat from a slab, we have the inverse of that with radiant cooling. And we could talk about those actually. So one of the limitations, again, we go back to ASHRAE 55, limits the temperature range. It's got to be greater than 66. That's your floor surface temperature, and of course less than 84. We already talked about this one, but this is the other one. So no less than 66. So that's our bottom line. So how much cooling can we actually do with a surface temperature of 66? Well, let's look at it. In the floor, if I'm in heating mode with 84-degree surface temperature, I can get outputs of 31 BTUs per square foot. In cooling, 12 BTUs maximum. So we have limitations of capacity based on surface temperature and based on condensation levels. So it's one thing to get the floor to this temperature, but it's another thing to make sure that we don't cross the dew point. Same thing with the ceiling. A little bit better on the output. Again, so even the B214 chimes in a little bit on this. Surface temperatures of ASHRAE 55 just refers to ASHRAE 55, 66 in occupied areas. And to prevent condensation, any cooled radiant surface, the supply water temperature for a radiant cooling system should be a minimum of 3 degrees Fahrenheit, 2 degrees C, above the anticipated space dew point as per manufacturer's instructions. Okay, so how do we do that? So, well, number one, we're going to have to know where the dew point is. So we're going to have to sense temperature and humidity in the room and understand where our dew point is going to be and modulate our chilled water accordingly. It's getting to be a lot of work here, control-wise. For your house, with your hardwood floor, and your latent load, and is it great for a home in certain applications? But the amount to set it up and be safe with it and maintain this, and you'll see this all over the place, 3 degrees above the dew point with the circulated water temperature, that changes, just as humidity changes in the room. So it's a complex thing to do. So if you have an airport, for example, lots of glass and people walking around, everybody's got the shoes on, and you've got a lot of surface area, and that surface area is quite conductive, you've got a fighting chance dealing with a sensible load in an airport, or there's all sorts of sort of commercial applications I can see for radiant cooling. And those are normally used with dedicated outdoor air systems as well, so makeup air and ventilation air, and what they do is deal with the latent load within the ventilation requirement for the people. So residentially, I know that some people are doing it or trying to do it and so forth. All I'm saying, be careful. You really got to know what you're doing. Any questions about radiant cooling so far? Anybody ever thought of trying it, or? Sorry? What's the advantage? What's the disadvantage? The complexity of setting up the controls, the limitation of output of radiant cooling compared to an air version. So in the sorry. Sorry. One. Oh, leaks. Well, you know what? The leak part of things, we got radiant piping and slabs. People worry about that. You know what? It's in a concrete slab. That's probably the best protected pipe in the house. There's plumbing pipe. That's a closed loop. You know, if that ever fails, then you got 15 psi in there with a slow fill, if a fill at all, compared to a plumbing line. You got plumbing lines going everywhere. That could flood your house as easy. So I don't know about worrying about radiant systems with respect to leaks. I don't think that's a factor, really. So the biggest negative is we're not dealing with the latent load. Radiant cooling is dealing with only the sensible load. It's not dealing with the moisture and the mugginess in the air. And the output. We can get a lot more cooling capacity out of moving air than we can out of a radiant surface for cooling. Now certainly you can put cooling into air, obviously, using hydronics, heat pumps, air to water heat pumps, go into a fan coil, but you're cooling water, but really in that case you're cooling air, and now you're dealing with the latent load, etc. But as far as radiant cooling goes, those are the negatives. Does that answer that? Kinda? Okay. Okay. Boilers. Okay, here we got the energy code talking about efficiency. So 936.3.10 electric boilers. So less than 300,000 BTUs in electric boilers must have an automatic water temperature control. Well, for God's sakes, I hope so. I don't know that they had to mention that, but it's in there. Gas-fired boilers, less than 88 kilowatts. AFUE of 90%. So, and if you're over 300,000 BTUs, you're down to 83%, which is non-condensing. I don't know if you guys know, a condensing boiler would be, any condensing appliance is going to be over 89%. So what they're saying is we want you to use a condensing appliance and we want it to be at least 90% efficient. If you take a condensing boiler and tie it onto a radiant floor where your return water temperatures are very low, you can run up to 98% with a lot of the products available right now. So 90% could indeed be the low end. Oil-fired boilers, so we don't see a lot of those, but Vancouver Island, etc. What can you do there? It's 85%. It's non-condensing. Your classic condensing boiler, I don't know if that's Triangle Tube or who that is. Combustion efficiency is above 90%. So most of these are wall-mounted boilers. There is condensing boilers that are floor-mounted, and certainly there's condensing boilers that are commercial, that are floor-mounted, large boilers, all varieties of condensing boilers. But anything residentially, these things you can get up to 399,000 BTUs in a condensing wall-mounted boiler. Why 399? Why not 400? At 400, there's a different classification as per the gas code. 400,000 BTUs, now you need an A ticket, it's not your average B ticket that can work on that boiler. It's got a power burner, and the code says anything over 400,000. 400,000 or over, thou shalt have an A ticket. Most gas fitters, there's a handful of guys in BC that have an A ticket. Most gas fitters are B tickets. So why not make your boiler $399 as the largest? These go anywhere from really 50,000 to $399 in a wall-mounted version like this. Usually low mass, and by low mass I mean back in the day, of course, we'd have the Wheel McLean cast iron boiler sitting in the basement, big heavy thing with cast iron sections, one after the other, water flowed in the bottom. It's a big container made out of cast iron. That's a high mass boiler. These things are very low mass. Most of them stainless steel heat exchangers. They have to be because they're condensing. So the act of the combustion process means you're going to condense the flue gases, which means you're going to get a very acidic, latent exchange of energy from the flue gases as a final touch to your hydronic water inside of the heat exchanger. So for the most part, made out of either copper, 90% of them stainless steel, but very low mass. So when you're trying to heat water that quickly, the water passages are very small. So it's a lot of flame and very little mass of water. Modulation, up to 10-to-1 turn-down ratio. That's fairly common. So if it's a 399,000 BTU boiler, it should go down to 39,900 BTUs. Yeah? 10-to-1 turn-down ratio, 1/10 of the capacity. So it'll modulate in steps. And that's kind of critical. We'll talk about that actually shortly too. But so in order to, there's one thing, there's combustion efficiency. 90%. Hey, great, because we're used to, until the last 20 years really, we're used to just standard efficiency, NAFA, B-vented appliances that just rely on convective heat exchange. So now we've got fans to induce the combustion process. We're scrubbing all the heat we can out of there. We're winding up with very cool vapor and water, the result. So these things all have condensate drains out of the bottom of them. So that's one thing. The efficiency of 90%, hey, great. We went from, 82, 85 to 90 or above. That's a good step. Is it the best thing in the world? Well, I don't think so. Actually, I would buy this boiler more because of that turn-down ratio. When I buy that boiler, what am I going to size it for? I'm going to size it for, the coolest day. The code's going to tell me to do that, especially CSA F280. So you got to size your appliance, and you don't want to oversize it. You want to size it for the job. So let's say your load is 100,000 BTUs. Okay, I got 100,000 BTU boilers. But our design time, how often are we actually at 100,000? Well, if your load is 100,000, it's 90% efficient, so our boiler would be 110,000 input because it's 90% efficient. So our output is 100,000. If our requirement of our heat load is 100,000, our output of our boiler, not our input, but our output of our boiler is going to be 100,000. So that's all great. So we address the coldest day of the year, which happens, that coldest day is actually every couple of years. That's the way we sized our boiler. But how often are we actually there? Like 2% of the time, we're actually at a design temperature. The rest of the time, we're somewhere below that, and usually below half of that. Correct me if I'm wrong at any time, David. So that's the nature of this guy here, 10-to-1. So it's a 100,000 BTU boiler, but it's also a 10,000 BTU boiler. That's the beauty of it. Forget about the combustion efficiency. How about we load match? How about we ramp our boiler down? Because in the old day, you're going to have your boiler that comes on. It's a 100,000 BTU boiler. It's a 100,000 BTU boiler. It comes on. You might have one radiant zone open. And out of a 5,000 square foot house, you might have one radiant zone that opens, and it actually cools the supply water temperature down. So the boiler aquastat says, click, yeah, I'm below my set point temperature. I'm going to come on. What I'm going to come on with? 100,000 BTUs to deal with, say, a 5,000 BTU load. Load matching. Very, very critical. So this is what condensing boilers do for us. This turn down ratio, very critical. So let's say you had one of these, and then you had another one of these. Let's say your load was 2 of these boilers, or you use smaller boilers. Now you'd have 2 boilers which can communicate. They will link together, and they will take turns, and they will also modulate their own burners to their most efficient level, so that now you take your 10-to-1 turn down ratio and multiply it by 2 different boilers to hit the sweet spot of operation. So yeah, 90% or 95 or 96, that's great, but I like this part of things. Of course, they use plastic or stainless venting. You've seen that, I'm sure. Condensing boilers. So we have plastic or stainless venting. Believe it or not, plastic's very expensive. The 636 is expensive. There's different ways to do it, Durivant, etc. All pretty pricey at the end of the day. And geez, and the manufacturer says you can just pop this thing through the wall. And that's the way it's done a lot in Europe, actually, isn't it? But here, let's just go through the roof, especially if it's new construction. Most of them have the venting range to get through the roof. So if somebody's telling you, no, it won't work, I got to go sidewall. I mean, that sidewall vent is there forever. And it's going to steam up the side of the house, your soffits, your windows. You got to have the clearance of windows and all. When you think about it, why? Why are we doing that? Why didn't we just go through the roof? Is it really that far to go? Sometimes you got to upsize the piping or whatever. There's a little extra cost, but for God's sakes, put it through the roof. Because those things are such low mass, they usually have a dedicated circulator that does only the heat exchanger of the boiler. So in the situation where you have the 5,000 square foot house and one zone open, that's not a lot of flow either, is it? In fact, that 5,000 BTUs is below a 100,000 BTU 10 to 1 turn down ratio. It's only 5,000 BTUs. So we can't be slowing, you know, if our pump is sized to flow a whole house and we only flow a fraction of that through the boiler can't deal with this flow doing this. The boiler says, you give me a good constant flow, you size a pump that can deal with my heat exchanger, and I'll modulate accordingly. So that's what we want to make sure we do. So that means if we're using a dedicated pump for the boiler, let's not try to go out and do the whole house with it either, because it's sized to do the pressure drop of the boiler, not sized to do the pressure drop of the house. Use the outdoor reset function built into the boilers. That's the other critical thing with respect to load matching we'll talk about in a few minutes, I hope. Run them as cool as possible. So do we want to put, because these things condense with a return water temperature that's below 140 F. So that's kind of tricky. Those baseboards, you know, they're 180, 190, whatever. Some of the convectors, they're higher supply water temperatures. Radiant floor, however, we know we're not going over, say, 130, because our surface temperature limitation, so 130. So if we have a 15-degree temperature difference in our design, that means we're coming back with fairly cool water. So that's great. The condensing boiler loves that return water to be cold. Combustion process really condenses them. If you retrofit a building and it's all baseboards and you just crank that thing to 180, you do not have a condensing boiler. You do not have a 90% efficient boiler. You've got a standard boiler that's running about 85% efficiency. Kind of waste of time. The only thing you do have there is the load matching, though. So run it as cool as you can. So address the loads accordingly. So, for example, if I had a radiant wall, and like I said, I got to radiate heat through drywall. So I'm going to have slightly higher temperature because I can probably get through this concrete floor easier. That underfloor stuff, we already said that's going to be hot as hell. So we need to circulate cooler water to the radiant floor and hotter water to the radiant ceiling or to a fan coil. That takes hotter water as well. So let's separate those loads. And when radiant calls, for God's sakes, let's bring that nice cold water back. When fan coil calls, okay, well, we send out the hotter water and we're condensing less. But do what you can to make sure that the system is running as cool as possible. Use clean water. I said it's low mass. The boiler is low mass. They're very fine in the heat exchanger and stainless steel. Don't just, have miles of radiant pipe and nobody put a cap on it, and hook it all up and then just run this water through with a bunch of gunk and whatever you filled the system with, because it's going to clog up that thing. It's not like the old cast iron boiler could take anything going through there. These are very particular to nice clean water going through them. Electric boilers. Why not? So what is it? It's really a box, a steel box with a bunch of elements in it. It's compact, it's wall mounted, it's simple, there's not much to it. Usually what I'm calling a medium high mass, because it is a steel container and it holds a volume of water and it's got immersion elements, something like a mini hot water tank with a lot of power. These things, the way they make them now, this rascal right here is actually a Tecmar control, but so they usually modulate with SCR or staging controls of some sort. This boiler, let's say it's 18 kilowatts, it'll have at least 3 6 kilowatt elements in it. So by the same principle that condensing boilers want to modulate, we should modulate these too. You don't come on with 18 kilowatts every time. You want to slowly bring that up and adjust for efficiency. So we say we're 100% efficient. Yeah. There's talk about exergy and elements and so forth. I can't really go there. But for the purpose of this conversation, it's 100% efficient. You put in a kilowatt of heat, you should get, or a kilowatt of electricity should give you a kilowatt of heat out of it. Now, I'm not saying it's cheaper, 100%. We all know what the price of gas is now and the price of electricity. 10 cents a kilowatt. If you got that in your house, you're in the 10 cents a kilowatt bracket for sure. Nobody's paying 8 cents or anything like that when you got one of these in your house. So they make them quite well these days. They're simple, not much to go wrong really. Of course, there's no venting and no gas line. You don't have to worry about that. You do have to, however, worry about an electrical service. So there's a time and a place for everything. 200 amps. So if we said 3,000 square foot house, I'm just ballparking 18 BTUs a square foot here. You're going to wind up with 16 kilowatts, which is 69 amps of power devoted to your heating. If everybody's good with that, I'm good with that. I don't know what else you're doing with the house, but you got 200 amps. Maybe you got 400 amps, in which case you don't have a problem. But with 200 amps, you're going to want to look at this very closely. Let the electrician analyze that very closely before you get into buying one of these rascals. Other than that, it's actually not a bad idea. Vancouver's leaning towards electric everything, and so it's either. Here we go. Okay, David.
Just so you know, right now, that heater is 100% efficient. That's non-negotiable. You get a gas boiler in there, it's running 95% give or take. At the current rates delivered to your doorstep, you're going to get whacked 3 times for that than you would be for a gas program. So anyone who goes down this path better do it with their eyes open. Your first tier power, which is 8 cents to stop quoted, is gobbled up keeping your beer cold and the lights on. Everything else is power above that, and this sucker is going to hammer you.
Keep that in mind.
I work for the gas company. I'm just a cheap bugger.
Okay, it's also low maintenance. Combi boilers. When we call it a combi boiler, we got to be careful. There's instantaneous water heaters, and then there's combi boilers. The boiler guys don't like the instantaneous guys calling their stuff boilers because there's different CSA regulations around boiler manufacturers as opposed to water heater manufacturers. So we're talking about combi boilers here. Also very low mass. What they have inside is normally a heat exchanger. So you got a boiler that's doing space heating as well as domestic heating, usually with a built-in heat exchanger. You're there anyway, you already got the one burner. Let's just turn on a pump and circulate to a heat exchanger, produce domestic water instantaneously, or let's produce heating water on the other side. Europe's chock full of these things. They think we're in the Stone Age with our storage water heaters. I had a guy stop by my office from Ireland, and he said he was just shaking his head. Anyways, they have a large BTU output, so no longer are we sizing these things to the heating load. So if my boiler is doing, let's say, space heating, it can also do domestic heating through storage. But when we're heating water instantaneously, which is what we're saying we're doing with this guy, part of it's doing the house load. So let's go back to the heat load of that house was what, 53,000 BTUs, let's say. So that boiler is going to be 150 to 230,000 BTUs. And so you go to put that in your home, it's going to have that capacity. Even though your heat load is 53,000 BTUs of your home, you're still having to put that in because what you're doing is heating water instantaneously. You take water from 50 degrees Fahrenheit and raise it to 140, which the plumbing code says you have to do, takes a lot of BTUs. You have only one kick at the cat. So that heat exchanger is large, it's very fine, and you're devoting all of that 180,000 BTUs to heating water instantaneously. Bigger gas lines, that sort of thing. Water quality alert. I'm just saying, you've got, where are you? Whistler, they've got some hard water, depending on where you are there. We've got fairly acid water all over the province. You really got to think about where you are and what you're doing, where your water's coming from. Is it coming from a well? Is it got, iron bacteria or any issues like that? Again, very fine heat exchangers. If you have a lot of hardness in there, where is it going to precipitate out? In those heat exchangers. I mean, in a closed loop system, you fill it once, and really you don't want to fill a system with hard water, but you've got a closed loop. You're not introducing this hard water all the time. When you have putting domestic water as an instantaneous heater, whatever's in it, you're doing it every time. So they have little filters on these things. Got to maintain them. But just be aware that if you're going to precipitate, calcify your heat exchanger and so forth, it's going to be very difficult. And what you might want to do, even on instantaneous or otherwise, is crack open the instructions and look at what it says about water quality and warranties. Yeah, so that's the other thing, is the output limitations. So because we're heating water instantaneously, we already know we're taking like 200,000 BTUs to heat this water instantaneously. And when we do that, what do we got? 2.2 to 4.3. The literature I looked at, all the different ones, the different varieties. So the biggest one, you're up around 4.3 gallons per minute. Okay, well, how much water is that? How much water is 2.2? Well, let's think about it. Shower head by code has got to be what? 2.5. So, but that's all the water coming out of the head. So when we size these things, usually 1.5 on the hot, 1.5 on the cold. So let's say it's 1.5. One shower head, 1.5. So we've used up 1.5 of our 2.2 with one shower head, in theory. Now, it all depends on a few different things, and what temperature and how much of the actual volume you're using. But if we got to size it by something, let's say 1.5. Now, that's per single shower head. Seems to me a lot of bathrooms have got multiple rain heads, and you have the body sprays over there. Oh, so the body spray, that's a shower head. That could be 2.5, couldn't it? So that's 1.5 there times, I got 8 body sprays in here. Wait a minute, that's a lot of water. Or how about my Roman tub filler? Let's crack that rascal open. And you take the strain out of there because you want to see that tub fill quicker. You crack that hot water valve open, and you can see that thing have straight cold water coming out of it with the amount of flow. And then you got to modulate it back, and then feel that water. Oh, there's the hot water. So it's a limiting factor is the output. So again, in Europe, they love these things, but we're a little bit different here. We're larger homes, or they got bathrooms everywhere and so forth. So it's a slightly different application. So I'm not saying this is a bad idea at all. I like it in a lot of ways, but we need to understand the limitations around everything. Water quality and output. And how are we matching it with the load of the house? Recirculation lines, how about that? Jeez. Okay. So you guys know what domestic recirculation lines are? If you don't put up your hand, domestic hot water recirc, simply a pump that is circulating water from the farthest part of the house, so you have instant hot water at your faucet. You got to keep that water flowing all the time. So the water's flowing all the time. In a tank style, well, what's the big deal? You just circulate to the actual tank, and you're circulating the tank. But when you're heating water instantaneously, it's flow sensitive. At 0.4 GPM, the burner comes on, comes alive, and it modulates down, and it wants to heat water. Because you might be cracking open a kitchen faucet for 2 seconds, or a bathroom, or their own tub filler. Who knows? It has to modulate the burner. So now if you take a recirculation line, run it all the way to the end, put a pump on it, and you tie it back into this heater, the whole point of instantaneous water heating is to have the thing shut off and not do anything when you're not heating water. So if we start recirculating, which I don't believe they do a lot of in Europe, now we're going to have this thing flowing through there all the time. So now the thing's waking up and going to flow, and so it's kind of on all the time. Defeats the purpose. So then they say, well, you know what you could do? You put a little tank right beside that, electric tank, electric hot water tank, like 10-gallon, a few $100, put it there. Hey, you could even plug it in or whatever. And so what you do is you circulate to that tank instead. So you circulate the whole house to the tank. I'm thinking that's in the drawback category because we just bought an instantaneous heater, so we didn't have to have a tank. So it's acting as a bit of a buffer tank there. So there's these little add-ons that you got to think about. Do you need a recirculation? Is your house big enough that you need a recirculation system? Think about all these things when you're deciding whether or not you want to use instantaneous water heating. Yep.
One question that regularly comes up. We are spoiled to having the tank. These are, say, not quite as nice. Could you discuss the pros and cons of having an electric tank downstream of one of these things to act as a buffer that would give us the tank-like performance but still producing the major load on the gas?
Well, I think the con I see is the simple fact that you have to buy another tank. So you're really just getting into the storage tank. You're utilizing the storage function. So that's a con in my mind. The cost of it, once you add up the negatives here, and then throw on the tank on top of that. I mean, if it has to be done, it has to be done. And there's each of the manufacturers of these say how they'd like to have the recirc done. They know this is an issue and they've adjusted their controls accordingly. But the most widely accepted way is to add a storage tank. So to me, what we're doing is we're blending storage and instantaneous heating, which defeats the purpose. If it's a smaller house and you don't need recirculation, you're going to be better off with this sort of application. If it's a larger house, recirculating everywhere, and we can talk about that soon too, then I'm thinking a storage style. We're not talking, and we will never talk about a gas-fired storage style hot water heater. It's coming up next. Actually, before we get out of heating equipment, we just talk about heat pumps, and I think we're probably running out of time here pretty quick, but air-to-water heat pumps. Anybody know about these? Anybody ever heard of a Daikin Altherma? Good, okay, we're fresh. So this is a heat pump, sits outdoors. This is refrigerant line sets that go to this indoor unit. They're calling it a hydro unit. And what this is a refrigerant. So it's a heat pump. It can either, if this was tied onto a household furnace, that would be your coil inside. So it's either switches to heating or cooling that coil. This, in this case, has a heat exchanger inside, which goes from refrigerant to water. So now we have water, either heated or chilled water. Kind of cool. So what do we do with heated or chilled water produced by a heat pump sitting outside like your classic air conditioner? We can go over, we can heat radiant floors. Remember, radiant floors are very low temperature, so the COPs, the coefficient of performance with these things, is huge. When you're trying to heat air, if this was the furnace and you had a coil in there, the temperature of the refrigerant you've got to get there is pretty high. When you're trying to heat this radiant floor, say to 85 degrees Fahrenheit, the performance of this goes up quite high. So these are actually a good unit. They're used also a lot in Europe right now and Asia. These guys got it tied onto a storage type tank. It comes with a control built in it with a sensor that says, okay, this is calling now, so let's switch our three-way valve and go off and heat this until it's warm, and then we can go back and do radiant floor or our fan coil or whatever else we want to heat or cool with water. Very high COPs in radiant water heating. Oh, inverter style compressors. Hey, so that is an inverter compressor, and this goes for all heating and cooling equipment when it comes to heat pumps. Inverter style compressors. Most of the Asian units, Japanese stuff, your Mitsubishi's, Daikin, Fujitsu, all the rest of it, have gone to inverter-style compressors. So if you have, say, a 5-ton, 60,000 BTU compressor, the old-school way, sitting outside, when that thing comes on, you hear this click, and the lights dim a little bit, and the compressor comes on. You're coming on with 5 tons of capacity all at once. And that's all that thing knows. There is some North American models that are 2-stage, so a smaller compressor and a larger compressor, but nonetheless they're, shall we say, single speed. Inverter style compressors, which this thing utilizes, which is why I like this version, inverter style compressors take single phase, convert it to 3-phase, and they modulate the electricity that goes into the compressor. So they modulate the refrigerant flow based on the load. It's got sensors in there and it says, okay, I got to do a lot of work or I got to do a little bit of work, and it'll modulate that compressor outside. It'll even modulate the condenser fan to what the load is. Super efficient. So I went to Daikin training actually in California once, and I'm not pumping up Daikin here by any means, but I was standing beside, they had the outdoor unit inside in the training room and then the fan coil right there, and they said, well, go ahead, what do you think of it? I go, well, turn it on, let's find out. They said it is on. Get out of town, there's no way. So the condenser fan wasn't even running. However, the inverter compressor, it starts at 0 amps and it sort of modulates up, and it was so little that I had to get the amp meter out and actually clip it on there. That thing's actually working. So this is years ago. And so but as you increase the load, it'll ramp up. So it'll match the load. So you can imagine the efficiency and reliability of that compared to Mr. 5-ton compressor. Bang, comes on, and 5 tons is too much. We're not load matching. We got 5 tons, but our load is 1.5 tons. So bang, comes on, and the short cycle shuts off. And of course, that's the hardest part on a compressor, starting and stopping. Inverter compressors have taken care of that. Super quiet. And you'll find these condenser fans, instead of always, they, for the most part, you can just about watch them go around. So there's great manipulation of refrigerant there. Just in case, back up electrical elements in these tanks. Also in the hydro unit here, 6 kilowatts, 3 kilowatts. No venting, no gas line, but you are using electricity, David, but a lot less. And of course you can switch to cooling. So we already talked about radiant cooling, maybe in the fan coil over here. This is tricky business. They come up to about 60,000 BTUs, so about 5 tons. Geothermal. Anybody put GeoExchange in a house? One guy? Okay. How did it work? Yeah? Good. Was it GeoExchange to forced air or to radiant? Okay. So for the purposes of this conversation, we'll be talking about water to water because we're hydronics. So we talk about water to water, ground source heat pump, water to water. So many ways to do GeoExchange ground loops, horizontal, vertical. We'll get into that in a bit. Oh, hang on. Oh, we got the wrong thing here. Anyways, ground loop types with geothermal. So we looked at the air source heat pump, and that air source heat pump is the same idea. The only difference is we blow air by the coil of refrigerant, absorb the energy, and transfer it into the house, into that heat exchanger in the house. So we're heat exchanging outside to the air, and then refrigerant to water inside. Here, we're saying, well, let's go with water outside, because we know water is a pretty good conductor. We figured that out already. So how do we do that? Let's put a whole bunch of pipe in the ground, different methods. This is called a slinky. These are usually up to, well, this one looks like an 18-inch pitch, so that'll be about 120 feet long at the most. I actually don't recommend this. These are side by side by side. That's one massive energy you're trying to take out of the ground there. But at least it's deep. Look at the depth they got here. This separation of single line, if this was 300 feet long, I would like the look of that. 300 feet there, 300 feet back, it'd be awesome. And then this sort of separation is great. However, these guys, little bit slack. I don't know what they're covering it with here, but not a lot of earth. Horizontal style stuff around here, you want to be like 4 feet for sure minimum, depending on what the properties of your soil are. The wetter the soil, the better. You got vertical borehole right here. And so if you don't mind these guys being in your yard in a retrofit or a new construction, then it's fine. That's a really efficient way to go. Certainly when you go horizontally with GeoExchange, you're a little bit more at the mercy of seasonal changes of soil temperature. So they can run a lot colder. When you drill down on average 200 feet here, the ground stays pretty steady. That is until we mess with it and draw the energy out of the ground into the water. And of course the water goes back into the home, into our water-to-water heat pump. One side is water to refrigerant, goes through the compressor, and then on the other side is a water-to-water heat exchanger. We're heating with radiant throughout the house. If that was a forced air unit, it'd just be water to refrigerant to air. We could spend a long time talking about geothermal. It's my particular favorite, but I think we're running short already. 10:16. What, Catherine, what time are we supposed to be done?
Yeah, we're going to
Breaks.
10:15.
10:15?
Yeah.
Yikes, 10:16 already. Okay, just some codes around GeoExchange. That's there, CSA 448-2. That's GeoExchange code. Appliances that are heat pumps are also mentioned in the BC 936. The same as air to water. Oh, I'd love to talk about controls, but I guess we're out of time. Yeah?
How much more of your presentation have you got?
I think it's not too much. Yeah, it's not too bad. Yeah, there's a fair amount there still. I'll just talk about warm weather shutdown quickly here. It's pretty critical. All these condensing boilers that we're talking about, even that heat pump has warm weather shutdown included in it. So have your contractor dial these things in. It's a big deal. So if we think about our efficient operation, we know our boiler modulates to meet the heat load requirement. So the flame will modulate. The BTUs will modulate to heat the requirement that it knows it has. So what is the requirement? So today, maybe it gets chilly tonight or whatever, your radiant heating comes on. Our design, once again, was for 130 degrees F in the floors. But do we really need 130 tonight to heat our house? I don't think, or let's say September 30. I don't think so. We could probably use about 79 degree water. You run 79 degree water through that boiler, it's condensing like crazy. You run it through that heat pump, whether it's geothermal or air source, it's really operating efficiently. So we have to tell the boiler what to do. We have to say that at 70 degrees, if my design water temperature was at the worst case scenario is 180 degrees, then that means if my design temperature outdoors is, let's say, 0, coldest day is 0. So at 0, I want you to be in 180. So compared to my minimum supply temperature, if I set my minimum supply, I can't heat it with less than this. This would be more for baseboards, from 110 to 180. But still, there's huge savings to be had. Number one, when it gets to be 70 or 68 or whatever this is here, tell the boiler to just shut off. How about that? And then when it says, okay, well, it's enabled because the outdoor temperature has dropped to this temperature, and as the temperature drops, tell the boiler to slowly increase the temperature of the supply water temperature. The cooler that supply water temperature is, the more efficiently everything operates. So when you set up the boiler, don't set it at 130 and forget about it. You've lost all the efficiency. You've got to set up the warm weather shutdown. And that means dialing in the minimum supply water temperature. So if we're doing a radiant system, it's going to be 75 F. I mean, if it's 70, the same temperature as the room, so it's probably not going to heat much. 75, let's say you start out, and let's say the maximum, depending on your load calculation, is 125. So that's your range. So you would start here. So you go 70 to 125, and that would be what's called your reset curve. Dial it in. So between load matching of your burner to heat to the temperature, tell it what temperature to heat to. Make sure it's as cool as possible. This is how you do it with these controls built into virtually every boiler I know of now, including that goofy electric boiler. So, okay, any questions? I guess I got to wrap this rascal up.
Scott, that's one of the most powerful presentations I've ever heard in this topic. It was rounded, it was thorough, very, very well.
Oh, thanks, David. Appreciate it. Thank you.